and for the radiation. And particularly, we talk about this particular discovery, which I think is extremely monumental, not just in physics and astrophysics, but across sciences over the last few decades. And a lot of people think that it's going to result in a Nobel Prize, which I think is very, very likely. Right, so I was told to give a talk on the detection of radiation waves, and I was told that people are going to concentrate more on the food, so I'll try and keep it not very technical. So I've tried to just step out most of the equations from this discovery, and I'm going to focus more on the animations and some sounds. Okay, so I understand that a lot of people here are not physicists, so I will start off by giving a very gentle introduction to what gravitational waves are, and towards the end of my talk, I'll try and discuss what statistical methods were used for the detection of gravitational waves and where we think that machine learning methods are going to be useful going ahead in this particular branch of astronomy. Okay, so let me start off by introducing gravity. So gravity is, according to Einstein's theory of general relativity that he came up with in 1915, gravity is basically distortion of space-time caused by the presence of massive objects. So there is this concept of space-time in physics. The idea is that we have a three-dimensional space and one dimension time, but they are not distinct, they are continuous. And because of the presence of massive objects, this space-time gets curved. And it's this curvature of the space-time that we perceive as gravity. Now, Einstein obviously was a genius, so within a year of proposing theory of relativity, he very quickly realized that if the space-time is flexible enough to be bent, then it should also be possible for massive objects which are moving to actually result in ripples and vibrations in this space-time which are propagating outwards. And these are the ripples and vibrations in the space-time that we call gravitational waves. So the general idea is that if you have a massive object which is moving very, very quickly, then it distorts space-time in a manner in which these distortions are carried in an outward direction and they carry the energy away with them, which are the gravitational waves. The problem, however, is that gravity couples very, very deeply with the mass. So the gravitational waves, just by leaving my hand over here, I'm producing gravitational waves which are going across the hall over here. But those gravitational waves are going to be extremely tiny, and there is no way we are going to detect those gravitational waves in the foreseeable future. So the gravitational waves that we are looking for are the ones which are extremely strong. And what sort of objects produce strong gravitational waves? So the idea is that if we have an object which is extremely massive, but whose size is extremely small, so you're looking for gigantic densities. And if those objects are moving very, very quickly, very close to the speed of light, then the gravitational waves produced because of that accelerated movement of very compact massive objects, those are the gravitational waves which will be very, very strong. So when we're talking about compact massive objects in astrophysics, then we're talking about things like black holes, which by definition are very, very small and very, very massive. You can have black holes which are of stellar masses, and you can have black holes which are absolutely gigantic, billions of solar masses. And then you have things like neutron stars, which carry the mass of like 2 or 3 suns, but they have a size which is like 10 or 20 kilometers, so extremely dense objects. The other requirement is that those objects have to move very, very quickly. So then we are talking about the objects which are whirling around each other. So we have 2 black holes or 2 neutron stars moving around each other and eventually merging together. And when they are very, very close, they are moving extremely quickly. So they are moving at something like 60 to 70% the speed of light. So those are the inspirals of compact binary objects that can produce the gravitational waves which would be as strong as possible, which we can ever hope to detect. So this is the general idea. Right, so in order to detect the gravitational waves, first we need to understand what is the impact of gravitational waves, what do they produce. So as the gravitational waves move through the space-time, what they do is they basically stretch the space-time in one direction, and they compress them in another direction. So we have a stretch in one direction, we have a compression, a stretch in one direction, and then compression in another direction. So you get a wobble in the space-time because of the gravitational waves, and anything which is present in the space-time itself. So here I have a demonstration of what would happen to the Earth when the gravitational waves are passing through the Earth. Now, just keep in mind that what you're going to see here is extremely exaggerated. The scale is extremely exaggerated, just to see what sort of things are going to happen when gravitational waves pass through the Earth. So here we have gravitational waves passing through the Earth, and you can see that Earth starts vibrating because of the presence of gravitational waves. Now obviously, the scale of the vibration is not something that is ever going to happen, no matter how strong the gravitational waves are. But that's the general idea. So these are the kind of effects at a very minuscule scale that we are looking to detect. Right, so that's where LIGO comes in. LIGO is the Laser Interferometer Gravitational Wave Observatory, which made this monumental discovery. LIGO is an observatory which is located here in the US. It actually consists of a pair of detectors. One of them is in Hanford, the other one is in Livingston. They're separated by 3,000 kilometers, which is important, and I'll come back to it why it's important. So each one of those detectors is actually an interferometer, and I'll explain in a second what interferometry is. The general, so basically they consist of two 4-kilometer long tunnels. Every one of this detector has 2 tunnels. And each one of those tunnels is 4 kilometers long, and they are arranged in L-shaped configuration. So you have one tunnel, and then you have another one which is completely perpendicular to the first tunnel. Right, and the general idea is that as gravitational waves pass through those tunnels, they change the length of those tunnels by a minuscule scale. And if we can detect this minuscule change in length of the tunnels, then we have detected gravitational waves, and that's what LIGO has achieved. Now, the important things to notice here that LIGO is unlike any astronomical observatory that has ever been built by us over the last 2 centuries. The reason is that we have actually observed astrophysics through observing the electromagnetic radiation, through looking at the stuff which is out there. LIGO is blind, and it is purposely built to be blind because electromagnetic waves are basically a source of noise, and we don't want that. So the way LIGO detects gravitational waves or detects objects is by listening to it. LIGO has ears. So it is a completely different form of doing astrophysics, and it is opening a completely new window for us to be able to understand the universe in a completely different manner. Okay, now let me come back to interferometry. So interferometry is basically the study of interference. Interference is a fundamental property of light, which basically says that if you have 2 light waves, 2 coherent light waves, which means that the wavelength of the 2 light waves are exactly the same, and if those light waves come together, if they recombine in such a manner that they are perfectly aligned. And what I mean by perfectly aligned is that if the crest of one wave lies on top of the crest of the other, and the trough of one wave lies on top of the trough of the other, then what we get is a resultant wave which has been constructive interference, which is called a constructive interference, which means that the amplitude of the resultant wave is going to be higher than the amplitude of the 2 waves which combine to produce that. On the other hand, if we have 2 waves which are completely misaligned, which means that the crest of one of the waves lies on top of the trough of the other, then they both cancel each other out. And the resultant wave has an amplitude 0, so we get absolutely nothing. So that's called destructive interference. And that's the general idea of interference. So where does interference come in this detection? So it comes in because LIGO is arranged as an interferometer. And so think of this thing here. So imagine that we have got 2 tunnels here. So this is one of the tunnels, and this is the second tunnel, right? And here we have the source of the laser, which go through this tunnel, which are actually going back and forth along these tunnels. So what LIGO is trying to do is, so basically we have a beam splitter over here. So as the laser passes through the beam splitter, one part of the laser goes through the first tunnel, the other part goes through the other tunnel. There are mirrors at the end of the tunnel, so the lasers get reflected, they come to the beam splitter, and part of the laser is then reflected towards the photodetector. And that's where the interference, the photodetector is trying to detect the resultant wave, which is produced as a result of interference of the 2 waves right over here. And the way these tunnels are set up is that if the length of the tunnel is precisely 4 kilometers, if there are no gravitational waves, no sources of noise, then the interference is destructive interference. There should not be anything detected at this photodetector. However, because of the presence of gravitational waves, the length of those tunnels is going to change. And when the length of the tunnel changes, we have constructive interference, or we produce resultant waves of different magnitude, and then we will have detection over here, and that will tell us that we detected a gravitational wave. So I'm going to run this demo, which shows you how all this setup works. So you can see these are the laser beams which are going through the beam, and now we have gravitational waves. As a result of this gravitational waves, we have this vibrations in the length of the tunnel, right? So here the waves are passing through the tunnel, they get reflected by the mirrors, and finally they recombine when they reach the beam splitter. And here we have a destructive interference because the length of the tunnel is exactly 4 kilometers. Now you will see that gravitational waves are coming in. And when the gravitational waves come in, there is a minuscule change in the length. And this minuscule change in the length results in interference. And then you get detection, a particular pattern of detection at the photodetector. And this is what LIGO attempts to do. Just to give you an idea as to how precise this measurement is, this is the most precise measurement ever made in the history of humanity. So the detection that was made last September, that changed the length of this tunnel by 10 to the minus 21. Right? So the 4 kilometer multiplied by 10 to the minus 21. That was the change in the length of the tunnel as a result of the gravitational wave. So even you and I changed in a scale by whatever our sizes are times 10 to the minus 21. It's absolutely minuscule. It's about 1/1000th the diameter of the proton. So this is how precise this measurement had to be. And we can do that because of this interference. Because the wavelength of light we can come up with use lasers which have very small wavelengths. So we can make this particular measurement. Okay, so as I told you that gravitational waves are actually not light. They are basically waves. They are like acoustic. We are trying to listen to these gravitational waves. And as it turns out, the sort of gravitational waves that light was designed to detect, those waves actually are in the audible band. So we can actually convert those gravitational waves into sound, into pressure waves, and listen to them, and try to figure out what the universe is telling us about. Right? And by listening to gravitational waves, we can actually try and learn about the sources, the objects which produce those gravitational waves. So here I have 2 examples. The first one that I'm going to play over here is a simulation of 2 stellar mass black holes, which are not spinning. The masses are about 1 solar mass and 3 solar mass. They are spiraling around each other, and eventually they are merging. So when that happens, what sort of sound are we going to listen? So here it goes. Okay, so that's what we call the chirp signal. So the chirp is, as you listen to that sound, what happened is that the frequency of the sound as a function of time was increasing. So these things are revolving around each other, they are coming closer and closer together, and as they are very, very close, they are actually revolving around something like 100 times a second. So they are revolving very, very quickly, and eventually that final whoop that you heard, that is merging. And once it merges, it settles down into one black hole, and the gravitational waves vanish. I'm going to play it once more. Okay, so that is a simulation of black holes which are not spinning, which means that the orbit, the plane of the orbit is basically, it remains constant, it does not change. But if the black holes are spinning and the spins are not aligned, then we get the plane of the orbit, which is no longer constant, it actually recesses, it changes, and when that happens, we get a very different sound, and that's what I'm going to play now. So again, stellar mass black holes, but this time the black holes are spinning, and the axis of the spin of black holes is not aligned. Had a similar kind of a chirping signal, the frequency was increasing as a function of time, but there was a modulation on top of that. So that gives you an idea that by listening to these things, we can learn quite a lot about the objects which are producing these gravitational waves. Okay, so So let me move on. Now let me discuss the first ever direct detection of gravitational waves. Now it's important to emphasize direct because this is not the first time we have actually detected gravitational waves. The gravitational waves were detected in the 1970s indirectly, which led to a Nobel Prize. So it was detected by observing what's called pulsars. But this is the first direct detection of gravitational waves. This is also the first direct detection of black holes. This is also the first direct detection of massive black holes. We always knew that these objects existed, but we didn't know, we had never done a detection of such massive black holes. Right, so the thing that we detected in September 14, 2015, that was a result of two black holes of around 30 solar masses revolving around each other, eventually merging together to form a black hole with a mass equal to 62 suns, 62 solar masses. By doing the analysis, we can find out that the signal came from us from about 1.3 billion light years away, and it dissipated gravitational waves carrying away 3 solar mass of energy. Now, just to give you an idea how much energy there is, this 3 solar mass of the energy that was dissipated, that happened over a fraction of a second, right? This whole merger that we detected happened in about half a second. So it was very, very quick. And just before the merger, in a fraction of a second, the energy that was released in gravitational waves, that energy was larger than the combined energy output of all these stars in the observational universe. So it was absolutely gigantic. And as I said, the signal that was produced by the merger of these black holes was about 10 to the minus 21. So this is what we call the strain. Strain is the fractional change in length of the objects as a result of the gravitational waves. So even though the energy was absolutely gigantic, the resultant strain was absolutely small. Right, so let me now discuss the signals themselves. So here I'm going to play another audio clip. So what you're going to hear is the actual signal that we detected and what it sounded like. And you will also see that signal in this what we call time frequency plot. So you will see the evolution of the frequency of the signal as a function of time in this particular plot. So what I'm going to play is initially I'm just going to play the signal as we received. It is at a slightly lower frequency, so it might be difficult to listen to. So it would be played twice, and then after that, we have actually moved the signal to a slightly higher frequency artificially, so that it becomes audible. Okay, so I'm going to play it now. There it goes. Okay, this is in real time, so you can see the signal was very, very quick. There are two panels here, one for each detector. And on the right-hand side, we have the actual signal that was detected by Hanford, Livingston, and then the two signals plotted one on top of each other. Let's now look at the signals in more details. So here are the raw signals as we detected them. So what's being done here is that from this particular signal, so this is the strain as a function of time as detected by the two detectors. The only filtering that is done over here is the filtering of the very low frequency and very high frequency components, because we know that they are noise. So those frequency components have been filtered out. So you can see that there is something over here. There is a very clear chirp signal which is increasing in frequency, and you don't really need any statistics. It's very, very obvious. If you plot the signals one on top of the other, we can see that they actually don't align. And the reason why they don't align is the distance between the two detectors, which was about 3,000 kilometers. So it takes light a maximum of 10 milliseconds to move from one detector to the other. And depending on the direction of the gravitational waves, that delay would be smaller. In this particular case, the delay was about 7 milliseconds. And that's why the two signals actually do not align. Right? When you get rid of this delay and then plot the signals one on top of the other, you can see that there is a very good correlation between the two signals. So that gives us a lot more confidence that what we have detected is actually not noise, it's a true signal, because it would be very, very difficult for some earthquake to come up with a signal. If there is a small enough earthquake that the detectors cannot detect, then it would be very difficult for that signal to result in a signal which is detected by both of the detectors with the same amplitude and to align very well. Right, so that is the raw signal. We did the analysis, LIGO did the analysis, and LIGO found the best parameters for the system that produced the signal. And we have the red curve over here is the resultant signal that we would get from those parameters if we solve Einstein's theory of relativity, Einstein's equation of relativity. If we filter out the low and high frequency noise components, then we get this green signal over here. And then if we plot the green signal, the green simulated signal, on top of the actual signal which was detected by one of the detectors, you can see that they align very well. So the theory predicts these signals with a very high level of accuracy. And we have done the same thing over here for the second signal. So everything works quite well. No statistics, no machine learning is required. All that is needed is just eyeball the signal and you have made the detection. Right? But obviously we do require statistics. Not in this particular case because the signal was very, very strong, but LIGO has been designed to detect signals which are at least an order of magnitude, and once the sensitivity increases further, 2 orders of magnitude lower than this particular signal, for which we do need good statistical methods. Okay, so what are the detection algorithms that are used at LIGO? First of all, there's a field of gravitational wave astronomy. I sort of say that this is like high frequency grading equivalent, right? Because timing is absolutely crucial in gravitational wave astronomy. We want to detect the signals as soon as possible. The reason is that gravitational waves, if there are black holes which are merging together, there will not be an electromagnetic counterpart. But if there are neutron stars which are merging together, there would be an electromagnetic counterpart. And if we can detect these things very, very quickly, in real time, we can actually provide triggers to electromagnetic telescopes for that to the follow-up. And that needs to be done very, very quickly. So for that, LIGO has come up with some algorithms to do low latency searches. And those algorithms are very simplistic. They are basically looking for some excess signal above some noise thresholds. They are not doing any kind of physical modeling of the gradation waves. They're just looking for some excess signal above a noise threshold. So once that kind of detection has been made, they want to figure out what is the significance of that detections. So they want to estimate the background. And that is basically done by, so let's imagine that LIGO has done the analysis over 16 days. So they've collected the data over 16 days, which was done in this particular case. Then what they do is they introduce a series of artificial time shifts. So you have the data from the 2 detectors. You time shift the data from one of the detectors by a time which is greater than 10 milliseconds. And 10 milliseconds is absolutely crucial because 10 milliseconds is the amount of time that light takes to move from one detector to the other. So by introducing this artificial time shifts, we are actually artificially increasing the amount of data that we have, right? And then by looking at signals in this, so we have collected 16 days of data, but by introducing artificial time shifts, we have actually come up with a data which spans over years. And then by looking at signals in that particular, in all of that time shifted data, we can try and figure out what is the significance of detection. So this is what's plotted over here. So here is the actual detection, here is some detection statistic, and this black curve is the curve which has been produced. So these are all the false positives that have been detected as a function of detection statistic. And the actual detection is over there. So in this particular case, it was about actually at least 5.1 sigma because we couldn't, the LIGO team couldn't find any signal with a significance as high as this one. So this is how the significance of detection is done. Right, so if you don't want to do low latency searches, if the time is not very important, then the actual main way of detecting gravitational waves is through match filtering. And match filtering algorithms in LIGO have been designed to target binary systems with individual masses between 1 and 99 solar masses. They have about 200,000, 250,000 template waveforms. Those are non-spinning waveforms. They take about 10 to 20 minutes for the detection to be done. And the parameter estimates are actually done by doing a fully Bayesian analysis. And this is where all the modeling of the physics of the gravitational waves is done. So this, in Bayesian analysis, what they try and do is they use Markov-Chain type of algorithms to come up with posterior distributions of the systems which are producing these gravitational waves. And as a result of that, you need to calculate the likelihood. In order to calculate the likelihood distribution, you need to calculate the actual predicted signal as a function of parameters, which involves solving Einstein's equations of general relativity, which are possible. So people have done a lot of work in LIGO to actually reduce the cost of both in terms of doing the numerical modeling of the general relativity and also coming up with very efficient Markov-Chain algorithms to do the analysis as quickly as possible. One of the techniques that is used quite a lot in astrophysics and gravitational waves is called nested sampling. Nested sampling is sort of an alternative to Monte Carlo algorithms. It's designed to do the Bayesian model selection. So it's designed to calculate the Bayesian evidence, but it can also produce posterior distribution. So most of my work in LIGO is actually in this particular area, coming up with, working with nested sampling algorithms to do the significance, to model the whole system. The problem with Bayesian analysis is that even though people have speed up the analysis quite a lot, it still takes order 100 hours. So you cannot really use those algorithms for low latency searches. They are very, very accurate, they are very, very robust, but they cannot be used to detect gravitational waves in real time. Right. So when I was working on this particular talk, and I was thinking about, well, I need to come up with some statistics and show some statistical methods which are useful for detection of gravitational waves, which was proven to be very, very difficult because the first detection did not require any statistics. But thankfully, just a few weeks back, LIGO announced the discovery of a second gravitational wave, which was detected on the Boxing Day. It was produced as a result of a merger of two black holes with a lot smaller masses. So this time, one of the black holes had a mass of about 8 solar mass, the other one had a mass of around 14 solar mass. They merged together to produce a black hole with a mass of about 21 solar masses, and it resulted in a release of 1 solar mass of energy in gravitational waves. Now the signal here was about an order of magnitude smaller than the first signal, which meant that very simplistic algorithms which are looking for gravitational waves above a noise threshold, they weren't able to pick it up. So it was very important to do the analysis using the Taptic tanks or Bayesian analysis to detect those particular kind of gravitational waves. So that's the second detection that LIGO was announced very, very recently. Sky localization. So sky localization is extremely crucial. As I said, electromagnetic follow-up of the systems that are being detected by LIGO is extremely important, which means that we need to give the telescopes, the electromagnetic telescopes, a location to look for. So if we can localize the sources very, very precisely, it's going to be obviously very, very helpful. The problem is right now, LIGO only has 2 detectors. So the way LIGO localizes the sources is in a very similar way to how we localize the sources. So if we hear a sound, we can sort of tell where the sound is coming from. And we can do that because there is a time delay. So depending on where the sound is, there is a time delay in the sound reaching one ear and then reaching the other ear. And using this time delay, we can sort of get an idea where the source is coming from. But since we only have 2 ears, our localization is actually not very good. And that's the problem with LIGO right now. LIGO only has 2 detectors. And because of the 2 detectors, it can only localize sources in this range. So the localization is not very good right now. And it's so basically we can tell electromagnetic telescopes a search area of hundreds of degrees, which is not very useful. But there are plans for additional detectors to come online. So in a few months' time, there is going to be a detector, Virgo, in Italy, which is going to come online. And the presence of the third detector is going to break this degeneracy. So you would have another ring over here, which is going to intersect that, and then you would have a very good localization of the source. There is also plans of, right now there is a detector under construction in Japan called Kegra, and there are plans for another LIGO detector to be built in India, LIGO India. And so once these detectors come online, then the localization will become very, very precise. Right, so when I first came across this image, I was astonished. So this image plots the sizes of the black holes that LIGO has detected on top of the map of the United States. So as I said, so this is the very first detection that LIGO made. So these things are gigantic, right? So this is about 62 solar mass. These two are about 30 solar mass. But look at the size of those things. Those are like 10 or 20 or hundreds of kilometers across. So these things are absolutely massive, absolutely dense. Here we have the second detection, and actually LIGO made a third detection, but we are not very sure whether it's a true detection or not, because the significance of detection is about 86%, and LIGO only announces discovery if the significance is about 99.9999%. So you can see that these things are absolutely massive. If you plot these things, so we actually knew the presence of some binary black holes through some X-ray studies. So we never detected black holes directly. What the way the black holes have been detected so far is by looking at the matter which is revolving around the black hole, and they release some X-rays. So by looking at the evolution of the matter around the black hole, we can infer that there is some mass right in the center, and then we can calculate the mass and infer that the mass should be very, very high. So these are all the black holes that have been detected, and these are the black holes that have been detected by LIGO. So these are completely new classes of the black holes that LIGO has detected. So it's the first direct detection of the black holes, and it's the first detection of absolutely massive black holes. And as I said, that these are not the gigantic black holes that we know exist, because the center of every galaxy has got supermassive black holes, which could be around millions of times more massive than the sun. And there are plans for having detectors in space, and if we get those, then we would be able to detect merger of this supermassive black holes as well. Right, so far I've talked a bit about the statistics. Machine learning, to be honest, has not played any role so far in the detections in LIGO, but that doesn't mean that machine learning is not going to be important. I think there are certain areas where machine learning is going to be extremely important going ahead in gravitational wave astronomy. So let me just present a couple of areas which I think would be very useful as an application of machine learning algorithms in gravitational wave astronomy. So the first one I have is what's called glitch detection. So one of the pains that LIGO has to go through is that Earth is a very noisy environment, right? So LIGO is trying to make this precise calculations of waves, but then it gets swamped by a lot of spurious signals. So you could have ocean waves, you could have earthquakes, you could have a plane flying around, you could have all kinds of those things which produce signals which may look like a gravitational wave. And these are called glitches. So these are non-Gaussian transients. One of the advantages of having multiple detectors is that you can actually rule out quite a lot of those things. So if we see one of those transients in one detector and not in the other, we can rule it out. That cannot be a gravitational wave. Because if it were a gravitational wave, then that should be a signal in both the detectors. But there are so many of them that by chance there is a possibility of both the detectors actually have independent sources of these transients which just happen to lie at the same time. And then is a problem. So actually LIGO collects a lot more data about the transients than it collects the data about the gravitational waves. It has about 200,000 channels which are dedicated to detecting those kind of transients. It has a slew of detectors. It has magnetometers, it has seismometers, all kinds of things to detect those things. But then the analysis is swamped by the amount of data that is involved over here, right? 200,000 channels, just imagine how much data you would have, and then you would have to figure out whether this is a true positive or false positive. So I think this is where machine learning techniques could be very, very useful, and people have already applied machine learning techniques. People have applied neural networks, support vector machines, random forests, and in order to try and build classifiers to figure out whether whatever they have detected is actually a gravitational wave or it's just a transient. So just to give you an idea what they look like, so here I have the actual gravitational wave signal that was detected by LIGO. It's a very typical signal. So you see as the time goes by, the frequency increases. Okay, so you can, and these are the detectors. So they are pretty much coherent and they look like gravitational waves. And this is a transient, it's called a blend. You can see that it's slightly different from the two signatures that we have over here, because this is like symmetric. Right? While gravitational we don't expect them to be symmetric. So this is just one example. So by training machine learning algorithms for glitch detection, I think we can make a lot of progress. And that will be extremely important once we try and detect, once the sensitivity of LIGO is increased such that it's going to detect low mass systems. If it's trying to detect merger of binary neutron stars, which is going to produce signals which are not going to be as strong as the one that I've just shown you. Another area where machine learning can be very, very useful is in order to do electromagnetic follow-up. So as I said, this is a time game now. So if we want to do electromagnetic follow-up, we want to make the detections as soon as possible. So here is an example. So if we are looking for the merger of binary neutron stars, what happens is the binary neutron stars are whirling around each other. Eventually they come together, and when they come together, they release a lot of energy in the gamma rays. So gamma rays are extremely energetic and electromagnetic radiation. And we can actually detect those gamma rays. But those gamma rays are released in just a few seconds, or sometimes 0.1 second after the merger. So we need to be very, very quick in order to catch the gamma ray glow of these systems. And this is very important. The reason is that we know very little about binary neutron stars. We know that they release gamma rays, but we're not entirely sure of that. So it would be extremely important if we can actually study those systems in real time, catch the gamma ray afterglow. For that, we need to be very, very quick in detection. Okay, so as I said, that there are low latency searches which have been designed for LIGO. There are low latency searches that can just localize the signals. Here, we don't really want to understand all the parameter space. We don't want to know what the masses of the systems are. What we want to do is we just want to figure out that there is a merger going on at this particular part of the sky, and then the electromagnetic telescopes can follow up, and we can do all the analysis on the sidelines after that. So there are algorithms in LIGO which are just trying to do sky localization as soon as possible. They are very accurate, but they are still not as accurate as a full Bayesian analysis is. The problem with full Bayesian analysis is that it takes a very long time, 100 hours. We can't use them. What are the possible solutions? As I said, one possible solution is to use this very rapid sky localization algorithms in LIGO, which are not doing any physical modeling. They are just trying to localize the sources by looking at the pitch and the amplitude of the gravitational waves. The other source, I think, would be if we can use code annulators. The reason why Bayesian analysis is very, very slow is because they are solving Einstein's equations of relativity. And they can take very long time. So they can take of order seconds to sometimes a minute. So even if they are taking seconds, and if you want to calculate those solutions millions of times, it all adds up. And that's why we end up with 100 hours. So here is some work that I did with some collaborators at Cambridge quite a few years back. So my main area at that point was cosmology, and cosmology at that time was at about the same stage where gravitational waves are. So in cosmology, we are trying to study the cosmic microwave background radiation. So that's the biggest data set that we have. That's the afterglow of the Big Bang. And what we are trying to do is we observe this power spectrum of the cosmic microwave background radiation. This power spectrum is very sensitive to cosmological parameters. And the cosmological parameters are like the dark matter density, the age of the universe, the matter content of the universe, and so on. So by observing the power spectrum, and then by varying these parameters with some kind of Monte Carlo algorithms, we can try and estimate the posterior distribution of those parameters. So it's very analogous to what we are trying to do in LIGO as well. In LIGO, we have the gradation of waves, we have the theory of relativity. Using the theory of relativity, we can try and figure out what is the masses of those black holes are, where are they located, and so on. The problem with cosmology at that time was that in order to calculate the power spectrum from the cosmological parameters, we had to solve a couple of Boltzmann equations numerically, and that was taking about 10 seconds, 20 seconds, 30 seconds. And as a result of which, the whole analysis was taking around 300 hours. So what we did there, we thought about it, we thought, why don't we try a neural network? Rather than using a neural network for doing any kind of pattern classification, we could just try and train a neural network to learn the cosmology, to learn the mapping from the cosmological parameters to the power spectrum. And if we can train a neural network to do that, once the neural network has been trained, it would do this calculation very, very quickly, in milliseconds. And then we can just use the neural network as a code emulator for solving this couple of Boltzmann equations and to speed up our analysis. And that's what we did. And it resulted in about 4 orders of magnitude speed up. So we went from 300 CPU hours to about 10 CPU minutes once the network was trained, and then we used the network just to do the analysis. So I think something like that would be extremely useful for LIGO to speed up the Bayesian analysis and come up with very rapid localization of the sources. Okay, so what does the future look like for gravitational wave astronomy? The first thing is, gravitational wave astronomy provides us with a completely different set of tools. So this is almost unprecedented in astronomy. It allows us to hear the universe, right? Which means that we would be able to detect things which are impossible to detect by just looking at the universe. We've already seen the example of it by being able to detect those massive black holes. The other discoveries that we are looking for are like stellar the merger of binary neutron stars, asymmetric supernovae. So these are like massive stars. At the end of their life, they just collapse, and it results in a massive explosion. And if the star is not completely spherical, and if it's rotating, then it will produce gravitational waves. Most of the interesting physics for the supernovae happens right at the core of the star. But that core of the star is buried inside thousands of kilometers of iron, silicon, and other elements. And there is no way in the world that we could see what happens inside the core of the star. But with gravitational waves, we can actually probe the core of the star as well. And I think the biggest discovery would be that we might be able to see what happens a few seconds after the Big Bang. So we know quite a lot about the Big Bang, but most of our information about the Big Bang comes from about 380,000 years after the Big Bang. At that time, the cosmic microwave background radiation was emitted. Before that, there is no light. So there is no way for us to directly detect what happened just before the release of the cosmic microwave background radiation. In particular, the current standard model of cosmology tells us that just a fraction of a second after the Big Bang, there was a rapid explosion called inflation. So the universe expanded by 60 orders of magnitude in a fraction of a second. Now that's a gigantic event, which means that it should have released gravitational waves. So it is a possibility that you might be able to detect those gravitational waves using LIGO itself. And that would be a monumental discovery. Right, so the other things which are happening, multiple detectors are coming online. As I already said, there is a Borgo detector which is coming online in Italy. There is there is a detector under construction in Japan, and there are plans for detector under construction in LIGO. So this field is rapidly expanding. And then there are plans in Europe to actually send those detectors in space. One of the advantages of gravitational astronomy on Earth is that unlike doing astronomy using electromagnetic telescopes, the electromagnetic radiation a lot of electromagnetic radiation is filtered out by our atmosphere. That's why it is very good to send the telescopes in space. With gravitational waves, we don't have that particular problem, but we've got another problem. Earth is a very noisy environment. Earth itself has vibrations and things like those. So it is useful to send the detectors in space for the reason that space is quiet. So we might be able to detect things which have got lower frequencies. We might be able to detect supermassive black holes which result in lower frequency. The other advantage of sending things out into space is that we are not restricted by a very small planet. So rather than having 4-kilometer long tunnels, we could have detectors which are separated by millions of kilometers. And by that, we can increase the sensitivity of those detectors as well. So there are plans in Europe to send a LIGO kind of a detector in space. It's called LISA. It depends on the financial situation, which right now is not particularly great. So I don't know whether it's going to happen, but we can read. And finally, I'll stop by showing you a simulation of two black holes which are spinning, and the axis of the spin is not aligned. And you can see when that happens, then you have precessing binaries happening. And I'll stop here. Thank you very much.